For a second type of potential energy, we have elastic potential energy. So elastic potential energy is stored energy, once again, but this time it's in the form of some sort of elastic. So for example, a spring, it can be elastic. A rubber band, anything that can be stretched or compressed can basically be an elastic. Typically springs, rubber bands, those are your two main examples. So here's what a typical scenario might look like. So we have a box connected to a spring, and this is at equilibrium, meaning it's 0 point, where it's neither stretched or compressed. So we're going to say x equals 0 centimeters. Equilibrium. We could pull this box out and stretch it to a distance, let's just say x equals d, or we could compress it and move it inwards, x equals d, a distance of d away from its equilibrium point. What we care about is how far we're moving it away from its equilibrium point. We're either compressing it or stretching it. Okay, so like I said, energy is stored in the spring. So our equation for this guy is potential energy elastic, so subscript small e, equals 1/2 kx squared. And sometimes you'll see potential energy as a u. That's totally fine. It's just another convention, like I said, of physics, just the way of writing notation. So potential energy elastic equals 1/2 kx squared. So let's go ahead and define our variables. K is the spring constant. It defines how stretchy or stiff the spring actually is. So you've noticed in our spring scales that we use, the 5 Newton spring scale has a really stretchy spring, and the 20 Newton one is a lot stiffer. So the 20 Newton one would have a higher spring constant K, and the 5 Newton spring scale would have a lower spring constant K. So this is dependent upon the stiffness of the spring. Okay, x in our equation is the displacement. So it's the displacement from its equilibrium point. So we can either stretch it out to x equals d, or we could compress it to x equals d. But it's how much the string is either stretched or compressed from equilibrium. X is not the spring length. It's only how far it's stretched or compressed. So for our units, we can take a look at this. We can see that the K is in Newton over meters, and the X is in meters squared. So you can see that, once again, just like work, we have a Newton times a meter, which gives us a joule. Okay, so let's do our first example. So let's calculate the potential energy stored in a spring that has an equilibrium length of 1.2 meters and is stretched to 1.5 meters. The spring has a spring constant of K equals 20 Newton meters. So basically our scenario looks something like this. So this is its equilibrium length. It has a total length of 1.2 meters, and then it is stretched to 1.5 meters. So its displacement is the difference between these, which was 0.3 meters. If you subtract 1.2 2 from 1.5. So for our givens, just X is equal to 0.3 meters, K is equal to 20 newtons over meters, and we want to know PE, elastic. So potential energy elastic is equal to 1/2 kx squared. We get 1/2 times 20 times 0.3 squared. And when you plug that into your calculator, you should get 0.9 joules. Let's do one more example. So a large spring has an equilibrium length of 3 meters, but is compressed to 2.5 meters. So its equilibrium length is 3, and when it's compressed, the springs are more tightly bound. So its delta X is how much it changes by, or just X, sorry. X is equal to 0.5 meters. So for A, we are looking for how much energy is stored in the spring if the spring constant is 200 Newton over meters. So we're given the spring constant, 200 Newton over meters, and we found X, it's 0.5, so let's find potential energy. You should get 25 joules. And then it asks, part B asks us, how far has the spring in A been compressed if it has 75 joules of stored energy? So it's the same spring, meaning the spring constant doesn't change. So K is still 200 Newton over meters. If you're working with the same spring, the spring constant does not change. But now our potential energy, it's giving it to us, it's 75 joules. And we want to know what is the length of the compressed spring. So X is what we're looking for. So let's go ahead and solve. And like always, I solve for my unknown before I plug in my givens. So I multiply 2 on both sides. That cancels this half out. We're left with 2PE equals KX squared. I divide K on both sides. We're left with 2PE over K is equal to X squared. Take the square root of both sides, and we get X is equal to the square root of 2PE potential energy over K. Plug in our knowns, and we get 2 times 75 divided by our K was 200. And you should get X is equal to 0.866 meters. The second part asks, what is the length? Oh, that's it. That's all it asks for. Oh, so how far has the string been compressed if it has 75 joules of stored energy? That would be 0.866. When it asks what is the length of the compressed spring, well, it's only asking what it originally gave in the question, which was 3 meters. That's the length of the actual spring itself. Okay.